right, so it is time to get started. I'm going to go over the solution of this homework assignment, and hopefully it's not going to take too long. Are there any questions before I, give you the solution of this particular homework assignment? Not a whole lot of questions. I did not. Sorry?
It was fun.
It was fun? Okay.
Yeah.
So maybe the next one is to write a program to do it autonomously.
No, wait. In Prolog?
It's just pattern matching, right? I mean, it really is just pattern matching for the most part.
It's going to be really hard to grade.
Mm-hmm.
It's going to be really hard to grade for you.
It'll be kind of interesting to grade. Okay, so the first thing I'll do is I will do the same thing as last time. I will go ahead and rewrite all of these in CNF. And then what I'll do next is to try a new way of looking at a CNF using a spreadsheet. So that will be kind of like a new kind of thing that I'm going to do. And hopefully it will help us get through a homework assignment like this one. Okay, so using a spreadsheet as a tool to help us find out what we can do for resolutions. All right. First thing first. This is not in CNF. We got to convert that, right? This one is already in CNF. This one is not in CNF. So we have to convert everything into CNF first. I'll use my mouse pad for this purpose. Okay, so here's mouse pad and double checking on the recorder. It is recording, so that's good. Okay. All right. So back to mouse pad. I want to convert every single expression that is given to be true into CNF first. And you can always concatenate CNF to make a longer chain of CNFs. Okay. So the first one is P implies Q. Okay. P is equivalent to Q, okay, which is not just P implies Q, because it is P implies Q and Q implies P. Okay. So we'll go ahead and do this all the way through. P implies Q and Q implies P.
Oh, mechanical equivalent or mathematical or mechanical?
It's just equivalent. It can be just a simple equivalence. It's fine. So in this case, this is not P. Oops, not P or Q, and then the other one is not Q or P. I'm using kind of a mixture of regular spelling of the operators and this negation, an exclamation point. Is that okay, or do you guys want me to spell out NOT?
That's good.
This is fine? Okay, this one is quicker. I just like it a little bit better this way. Okay, and we're done, right? This is already in CNF. Are there any questions about why this is already in CNF? It is a big conjunction of individual components. Within each individual component, it is a disjunction of either the negation or the non-negated version of a variable. In this case, P, Q are variables. This is already in CNF. Q or R is already in CNF, so that one is good. And we only have this last one to deal with, which is the negation of R and S. We can turn it into a CNF just by applying De Morgan's law once, okay? Because the negation of a conjunction we can apply De Morgan's law so that it becomes the negation to each individual component, but we have to change the operator from and into a or. Okay? So this one becomes not R or not S. Okay? So now we have everything put into CNF, and the CNF for the entire system, for everything, is really just chaining everything using conjunction. So the entire CNF is now not P or Q, and not Q or P, and Q or R, and the last one is not R or not S. That's the solution of step 1, I believe. Okay, is that okay so far? Okay, I'm hoping you guys all got this one right, because if you do not get this one right, the rest cannot be done correctly either. Yep.
Is it okay if you just included the not what you're trying to prove right at the beginning, instead of like just combining all through the steps?
That is actually step 3.
Yeah, I did it. I feel like I was repeating it. So.
Yeah, that's actually step 3, because if you go to the instruction here, okay, the step 1 is to turn the known facts, which are basically these 3 items, because we start off with the following known facts. And these are the 3 only things that we know about the system that has to be true. So I want to turn all of these into CNF first. So I can kind of see that your solution, if you already have the negated version of the theorem attached to it, you already know how to do step 1, but I actually wanted step 1 to be kind of by itself so that I can see the CNF all by itself first. So I haven't decided how to grade yours. Okay, step 2 is what we're going to do next, is to prove the known facts by themselves do not lead to a contradiction. We do not want a contradiction, because if these known facts is leading to a contradiction to begin with, there's nothing we need to prove, okay? Because nothing good can come out of a system where the known facts lead to a contradiction to begin with. All right? Okay, so this is when I'll start to use a spreadsheet to kind of do this instead of the usual way. So I'm going to use LibreOffice. Sorry?
Is it all?
Well, it's going to be interesting. This is the way I'm planning to do it. Whether it's a good way to do it or not, I don't know yet, because this is the first time I'm going to do it this way.
If you're being guinea pigs.
Well, SMI. Okay, we only got 3 variables. PQ, let's see, which 3 are we talking about? We have P, Q, R, and S. So there are 4 variables. That's okay, not a problem. So we have P, Q, R, and S, okay? And I'm interleaving because every other column is the negation. So we have not Q, not R, and not S over here. And then the next thing I'm going to do is I will make this a little bit more concise so I can bump up the magnification, like so, okay? So this makes it easy for me to express a single term within the CNF, because I just have to check off which one it has within a disjunction. And then the conjunction is implicit. It's basically looking at all the rows together. That's basically the conjunction. Okay. So let me illustrate what I mean by that. Okay, so I'm going to have to pop up the mouse pad on the other side so I can look at the equations on this side. And I'm going to have to reformat this a little bit so I can see each sub-expression, like so. And get back to the spreadsheet. Okay, so the first one has a not P, so I'm just going to check not P here. It also has a non-negative version of R, I mean the Q, so I'm going to put a check mark here. So that is one way to indicate this is not P or Q. Okay, so I'm going to do the same thing with the second row, or the second sub-expression, which is not Q or P. Okay, so I'm going to put check mark here for not Q, and then put one check mark here for P. And then we'll take a look at this one, is Q or R. So we have one check mark for Q, one check mark for R, and then the last one is negated R and negated S. So we have a one check mark here and another check mark over here. There we go. Are there any questions about how I'm using a spreadsheet to kind of keep track of the sub-expressions? Now, why is this useful? Because everything is lined up, right? Okay. So when you look at the expressions, if you find 2 x's within the same column, okay. So if you want to make it better, you can select these 2 columns, and you can change the color, change the background color to something. That doesn't work, right? Okay, we'll choose something else. Let's pick a different color. All right, we'll pick something that's slightly more neutral, and then we'll pick highlight these 2 too, so that it's just easier to see. And we'll pick another hue. Maybe that. Okay, that's not too bad. Okay, so this makes it easy to kind of visually spot, okay, which 2 sub-expressions can resolve. Are we kind of doing okay with this? It also makes it very easy to identify which sub-expression is resolving with which other sub-expression, because now I can just call out the row numbers and say I'm taking a look at row 2, and we can resolve it with row 3, right? Because in this case, you can see that there are two x's within the blue section, and one is the non-negative p, and the other one is the negative p. So that makes it a little bit easy to do the resolution. So I'll just go ahead and do it, okay? Because my objective is to systematically prove that this system of truth does not lead to a contradiction to begin with. So I'm going to have to do it very systematically. I will start with row 2 and try to match all the other rows with row 2. And then we'll start with row 3 and match all the rows after row 3 with row 3, and then keep doing this in the loop until I can systematically show that any new resolution will not end up with something that we have not seen before. Okay, so we'll start with row 2 and 3, okay? So if you look at these two rows, I really like this representation because I can now highlight stuff, and it's easy to see which two we are highlighting. And the result of the resolution is we can pick one or the other to cancel out, but then the other two we have to keep. So the result of resolving these two, if I choose to use P for resolution, then I end up with Q or not Q. So the result of the resolution is one here and one here. And I can even comment here, I'm so liking this format. Okay, so this is the resolution of row 2 and row 3. All right, I'm liking it. Okay, are there any questions about this particular representation? Okay, so I'm done with row 2 and 3. We look at row 2 and row 4. Can those two resolve? They cannot resolve because they both have the non-negative version of Q, and that doesn't work. Resolution requires one to have the negated, the other one to have the non-negative version of a variable. Okay, so I can now highlight 2, 4. It doesn't work, because row 2 does not have R, okay, and row 4 does not have. Row 2 does not have R. Row 4 does not have P, so they cannot resolve. They both have Q, but we need them to be opposite. And then you can look at row 2 and row 5, and these two resolve. Not even close. And then we look at row 2 and row 6, and these two resolve. Well, that's a new one, okay? They cannot resolve because this one just boils down to true, but I'm going to leave it here. So we are done with starting with row 2. Now we start with row 3, and we say, okay, can we resolve row 3 with row 4? And the answer is yes, we can, because one has not Q, the other one has Q, so we can resolve these two. And the result of the resolution is the Q's are gone, but then we have P left, and then we have R left. And this is from resolving 3 and 4, row 3 and row 4. Okay. So are there any questions about this process at this point? I'm sorry that I did not tell you guys about this technique because I just thought of it. Okay. As I was walking to the classroom, I was thinking, can I do this with a spreadsheet? Because it seems like I'm matching things, and with a table format, it makes it easy to match up stuff. And so it just occurred to me.
I just make the assumption that anything you have us do, we can do with a spreadsheet.
Well, spreadsheets are very, very useful, that's for sure.
That's why the assumption is made.
Yep, so we match up 3 and 4, so we look up 3 and 5. Can these two resolve? No, the x's are all over the place. They're not even sharing, a common variable in this case, so they cannot resolve. 3 and 6, it's not useful because 6 is just going to be canceled out to just a true, right? Because we have Q and we have not Q, it's just true. Okay, there's nothing, that can be helpful here. All right. So we'll go ahead and try to match up 3 and 7, which is not going to be very productive. Well, actually, yeah, it's not productive because they cannot resolve either. Okay, because this is the result of resolving 3 and 4 to begin with. Okay, so we're done with starting with row 3. Now we start with row 4. row 4 and row 5 cannot resolve. Well, they can actually. I take it back. Okay, these two can resolve because when you look at this color here, they can definitely resolve. So the resolution of row 4 and 5 is Q and not S. So we have Q and not S over here. And this is from 4, 5, resolving row 4 and row 5. So now we move on to row 4 and row 6. These two, well, it's useless to resolve it because row 6, okay, I should probably highlight row 6 because of that reason. So I'm going to highlight row 6 by changing the font color itself, just so that we know that this row is kind of special because it is just true, so it's not really useful for any consideration other than, oh, okay, that's the result of the resolution. Okay, so we are starting with row 4 and row 7 cannot resolve, and row 4 and row 8 cannot resolve because we were just there before. Okay, now we start with row 5. Are you guys kind of seeing the process? Okay, it's how it is kind of systematic. So we start with row 5 and then we match it up with row 6. Not going to work because we actually want to take row 6 out of consideration. This will resolve with row 7, right? When you look at row 5 and row 7, R is the shared variable. One is negated, the other one is not. So the result is we keep the not S here, and then we also keep the P over here. And this is a new one. We have not seen this particular combination before, so that's why we have to write it down. And this is between row 6 and row 7? 5 and 7. Okay. So row 5 and row 7, that's right. This is between row 5 and row 7. Row 5 and row 8 do not, share negated and negated. And then row 5 and row 9, this is just a newly produced, expression, so it's not gonna work. All right, row 6, we don't want to start with it. Now we start with row 7. So with row 7, row 8 cannot resolve. Row 7 and row 9 cannot resolve either. So as a final check, I'm going to start with row 1 again, just to double check and make sure that this is everything that we can do. Okay, there's nothing else we can do at this point. Okay, okay, all the ones that we have seen before, we don't have to deal with it again. So row 1, I only have to start with the new ones, the ones that we constructed. Row 1 to row 7, oops, row 2 and row 7. Okay, they do share one thing, so we can resolve these two to a R. So this is between row 2 and row 7. And then we look at row 2 and row 8. These two cannot resolve. We look at row 2 and row 9. These two can resolve, right? It resolves to Q and not Q or not S. And Q or not S is already resolved here. So we have done it before. This is a repetition. Okay. And that's it. Okay, we need to put it across here. Let me just double check row 2 and row 7. These two cancel out. Oh, we're missing one here. We're missing.
We already have that on line 4, don't we?
Sorry?
We already have that same thing on line row 4.
Row 4? Oh, you're right. Okay, so this one actually should not be here altogether. I made a mistake. The resolution, I missed one term in the resolved term. Okay. All right. So we start with row 3 now, and we only use the new stuff to test it. Okay, which is 7. 7 cannot be resolved with row 3. Row 3 and row 8 cannot resolve. Row 3 and row 9 cannot resolve. So now we'll start with row 4. Row 4 and row 5. We have done it already. Okay, so it's a good idea to keep track. Yep.
Why can't row 3 and row 8?
Row 3 and row 8.
Isn't there a Q and non-Q?
Well, we have the 9.
Yeah, we already have. Okay, row 3 and which one?
Row 8.
Row 8, these two? Okay, so Q and not Q will resolve, and then we have R and S remaining, and we got that on row 9 already. Yep. Okay, so where were we? I think we were on row 4 and row 7. Yes? No? That won't work. And then between these two rows, it won't work. Between these two rows, it won't work. Okay. Starting with row 5. Okay. We're almost done. We are almost there. Row 5 and row 7 cannot resolve. No, they can resolve. Okay, because we do have these two. And after they resolve, we end up with something that is already here. So we have row 9, as the result. Right? Okay, so that's nothing new. So take it out. That won't resolve. And that's the result already. So we already know it cannot resolve with row 5. Okay, starting with row 7 and row 8 cannot resolve. Row 7 and row 9 cannot resolve. And if you look at row 9 and row 8 and row 9 cannot resolve either. So we are done. We are done cross-checking every possibility and made sure that we do not come up with a new expression. I opt for more EVs on campus. So now we're done, okay? And as a result, did we get to a contradiction? Nope. Nope. And since we cannot get to a contradiction, we can now proceed to step 3 because the truth of this particular system is not leading to a contradiction by itself. Yep, go ahead.
Is there also a P and not P, just another truth that is not that we didn't have? From row 2 and 3, because you could apply that, you could do it twice. So is there another?
You can
truth?
apply it in a different way, but it's not going to help. Let me show you why. Okay, so if we resolve row 2 and 3, but in a different way, in other words, instead of canceling P, we can cancel out Q, right?
You just be left with P and not P.
Right, then we end up with just P or not P.
Which is the
But
same.
that's also a special row. I need to highlight this one with green also,
Okay.
because when you have P or not P, it is just true.
Right.
And when you have a true in a conjunction, it's not hurting it in any way, but it's not helping either, right? All right. Are there any questions? Now let's just take a closer look at what does it mean when we have these kind of interesting ones. So what does it mean when we have P or not Q and not P? I'm mixing symbols here, so let's try not to do that. So when I use those terms, I'm going to use the other not here. Okay, so let's look at these two and basically find out why does it boil down to just true. Okay. Well, one quick way to do it is a truth table. So now we have a truth table. And with a truth table, we can now quickly and easily see all the possible combinations between P and Q. Okay, with this one, they're both false. Okay, but that's okay because with each sub-expression, at least one of the term is negated. It will always catch the one that is false and say, oh, this makes the entire term true, this makes the entire term true, true and true is true. Are we okay with the first row? Yep.
If we didn't show the work for this, usually I just skipped over because I just assumed you'd know, so you wouldn't have to grade as much. Like if we didn't show the work for like that expression, like would it
Oh
be
no,
okay?
you don't have to show this one.
Oh, okay.
You do have to kind of show that these two can resolve, but except when they do resolve, they resolve to Q or not Q, or P or not P, and then those basically boils down to true. So you still have to kind of show that particular step. Okay, now between these two, okay, P is false, so that means not P is true. This one is true, and then we look at this one here. We have a P or not Q, and this one is false. Oh, okay, so this one it is possible for it to be false. But the step of the resolution just takes a look at resolving these two, and then the other two will join with a OR.
This was equivalent, so when they're different, it's false.
Right. And then these two would be false too, and this one would be true. I'm just trying to figure out, how we can take out this term altogether from the CNF. I'll have to think about this because the resolution step itself, says that we can resolve P. We can basically pick Q and not Q and resolve these into just P or not P, but that doesn't seem to make any sense in this case. So I'll have to think about it a little bit. Okay, I'll come back and give you the answer in the next class. But as it is, using the resolution step itself, we should be able to take out these two terms. It just kind of works out that way. Yep.
Like since we all kind of probably did it in a slightly different manner, like it's possible for like one of us to get like Q or not Q, and then another person to get maybe like S or not S, probably, right? Like depending on how we the systematic way that we each did it.
You can do it in a slightly different order.
And
right?
like even if it's like even like if it wasn't systematic, they eventually got to it. Like it's still correct, right? As long as you showed your work, right?
Right.
Okay.
Yeah, the order doesn't have to be the same. But I'll have to think about this one a little bit more.
Were you looking for all possible combinations in the homework? Because I didn't have P or not P, or P or not P. Would that be okay if I didn't have that one included in my step 2?
In your step 2.
Right.
I think that's what Vincent said as well.
Oh, okay.
Yeah.
Because we might have done like a slightly different, like I think I was talking to someone else, like I did it in a different, order, I guess, than someone else did it, and then like I was wondering because of that, and if I already concluded that it was a false, I contradicted it already, then I haven't reached like, that one step that he did like maybe in the beginning, then it's still a correct solution, right? Even though I didn't show every single possible like combination of
You
possibilities.
just have to make it to one contradiction. So as long as
Yeah.
you make it to a contradiction, it doesn't matter as long as you did it correctly. Yeah. Because the negation of the of S implies P has to lead to a contradiction somewhere.
Yep. Okay. I think I just spent a little bit more processing on what I said a little bit earlier. I think this is okay. I think it's okay for this to be considered true. Because this is the original expression, and then we end up with true as the resolvent. Okay, this is the result of the resolvent. So this is all one, right? Because if it's true, then it is true regardless of P or Q. But it has to only go in this direction. And false implies true is actually a true statement. You can imply true from false. So this resolution step actually, should make sense. No, take it back. Okay, the resolvent is P or not P, which is basically just true. Okay, that's fine. They're all ones. And when you're resolving, okay, when you have a resolution step, let's say we have psi inverse phi here. This is the syntactical transformation. But in order for the syntactical transformation to be semantically correct, it means that you also have to show that psi implies phi. But in this case, the implication does work. But then everything will imply this because it is all true. So I will have to think about this a little bit more just to be sure that it makes sense. Okay. Yep.
So the end result of all of this, though, is that it leads to a contradiction. It leads to a contradiction, right? So
there's no contradiction in step 2. Right.
we haven't even made to step 3 yet.
Nope, not yet. This is the basis of going to step 3. Okay, so let me just kind of move on to step 3. I'll come back with this one. I'll think about it a little bit more. Step 3 is to disprove or prove the theorem S implies P. Okay. So if I go back to the spreadsheet, well, go to the work mouse pad first. Okay. S implies P is the same thing as saying not S, oops, the other not S or P, which is already, this is already a CNF. Now I have to add this to the entire system and then do all the resolution again. But I'm not going to redo stuff that I have done already. Okay, so that's the thing that is nice. Yep, go ahead.
You need to negate that one first.
Sorry?
You need to find a negation of that one first.
A negation of?
S implies P. We try to prove it.
Oh, we need to negate it first and then put it in the system. Okay, you're right. Okay. So we have to negate the whole thing. So we'll go ahead and negate this whole thing. And after you negate this whole thing, you can apply De Morgan's law. So then we have the negation of S and the negation of P, which simplifies to just S and not P. And this all by itself is a CNF, so we can just add it to the spreadsheet. So S by itself is one column, not P by itself is one column. So when we integrate this into our current system, then we'll, okay, let me put this inside like that. So we will have, S here by itself, having a check mark right here. And then not P by itself is going to have a check mark, but on a different row. Okay. So now we have, a little bit more on the spreadsheet, and we want to resolve to false. Okay. In other words, we want to resolve to a row that has no crosses in it. That's basically the objective. All right. So let's zoom out a little bit so that we can see all of the rows. Okay, so these two are the only ones that are newly added. Okay, so what we can do is kind of shortcut the process and start with row 11, and then go back and see what we can resolve with. And the objective is we want to get rid of it altogether, right? So we can resolve it with this guy here. We can also resolve it with any one of these. We can resolve because this is S, and these three rows have the negative version of S, and then one already has a negative version of P as well. So I guess we'll resolve these two first. Yep, go ahead.
Back to step 2.
Back to step 2.
Or I think step 1. The Q or R. Don't we need to use De Morgan's law on that and get not Q and not R and put those into the system as individual variables?
Back to step 1.
I think. Yeah.
Okay, let's take a look at step 1 again. Okay, step 1. You mean with this one?
Yeah.
But Q or R itself is a CNF.
Yeah, but in addition to that, also use De Morgan's law and get not Q and not R, and put both not Q and not R individually in the system as well.
But why do you want to negate it? See, De Morgan's law only applies when you're negating a disjunction. But this is already a part of the known facts of this system, so there's no need to negate it.
But isn't not Q also a known fact of the system as well?
No, it's not.
Because if you use De Morgan's law, you get not Q and not R, and it's separated.
But you cannot apply De Morgan's law here because the known fact is Q or R, right? That's the known fact. To apply De Morgan's law, the known fact has to be the negation of Q or R. Okay, so if I give you, instead of that, if I give you, this is getting a little faint, I'm gonna put here. Okay, so instead of giving you the highlighted one on the projector, instead of that, if I give you the negation of Q or R, then you have to apply De Morgan's law and turn it into not Q and not R. Because the objective is to turn each and every single one into its own CNF, and then we just take a big conjunction of all the CNF to become the final product. But because this one is not negated to begin with, it is a CNF. If you just put parentheses around it, it is already a CNF, and that's why there's no need to. The De Morgan's law cannot be applied in this case.
Or maybe I'm thinking of the third line. not R, and that's
Right, that one does require the application of the De Morgan's law. But the result of the De Morgan's law on the third one is a disjunction. So it becomes just a term, and R and S, or the negation of both, they're not individual because they're not connected by a conjunction, they're connected by a disjunction. So is that helping? Okay. All right. So now that we got that cleared up, we'll go back here. So the first step is to resolve row 9 and row 11. So I'm going to write down 9 and 11 first. So if you combine row 9 and row 11, you can see that the S term is canceled out, and then we only have P left as the result of the resolution. And after this, it's easy, right? Because we only have row 12 and row 13 to resolve, row 12 and row 13, and they resolve to nothing because one has not P and the other one has P. So when you resolve these two rows, it becomes just false, which is our solution. We have contradiction. And because the negated version of the theorem leads to a contradiction, the theorem itself has to be true, because this is proved by contradiction. Are we doing okay so far with this? And I really kind of like this format, because it does not make it really long and have to wrap around, and also at the same time it makes it easy to kind of match the negated and the non-negated version of a variable. Are we doing okay so far? Yes. Yeah? Doing okay? All right. So if this is okay, I do want to skip a little bit ahead of time to talk about proof by contradiction, because I kind of felt that I, introduced proof by contradiction, but without really giving it a kind of formal treatment. So I felt that I should give it a formal treatment first, and then we'll kind of proceed and go back to talk about predicate calculus. So we kind of skip a little bit forward to proof techniques, and skip in here. I'm going to skip all the way to proof by contradiction, which is something that I just wrote not too long ago. You can actually check the timestamp. I wrote it 10 p.m. last night, so it did not exist before. All right, so proof by contradiction is kind of like this. Okay, so I have to kind of explain the term first. If we use a set S to be all the well-formed formulae that can be inferred in a propositional or predicate logic system, and at this point we're only concerned about propositional logic. This set can be infinite because you can keep inferring stuff from known facts, and there may be no end to it. Okay, but we'll just consider this set as all the well-formed formulae that can be inferred. Okay, it's one huge set with a lot of well-formed formulae. And what we'll do is, if you are going for a forward proof, that means eventually you can go to a step like this. In this case, we use phi, which is the funny-looking 0, as the theorem that we want to prove. So this means, if you take the entire set of every other formulae that can be derived, you only subtract phi from this whole set, that can infer phi. If you can find a way to do this, this is a direct proof. So a direct proof is a forward inference by using the inference rules. And the result that you want to get to is phi itself from something that does not have phi. Are we still doing okay? Are we doing okay so far with this notation? The symbol that looks like a T rotated counterclockwise 90 degrees, this one here, this is infers. Okay, so this is a mechanical process. If you take all of the other well-formed formulae that can be inferred, okay, with the exception of phi itself, if this entire set, huge set of well-formed formulae can infer phi, then this is a forward proof, also known as a direct proof. Okay, which is what most people like to do, because we like to walk forward. Proof by contradiction is interesting because proof by contradiction is going in the opposite way. So we'll get to that one a little bit later. Now, in a real direct proof, okay, this is the theoretical view of a direct proof, but in a more realistic way of looking at a direct proof, it's more like this. Okay, if you consider a set T of well-formed formulae, and hopefully this is a small set because otherwise you have to spend a lot of time to get to it. This set of formulae will at some point infer the theorem that you're trying to prove. That is, basically a more pragmatic view of looking at a direct proof. But nonetheless, okay, in a direct proof, the theorem that you want to prove, which is represented by phi in this case, is on the right-hand side of the inference symbol. Okay, you are actively trying to syntactically get to the well-formed formula phi. That's a direct proof. Are we doing okay so far with the concept of a direct proof? Okay. What about the indirect proof or proof by contradiction? Okay. In a proof by contradiction, we're trying to achieve something like this. Phi is still representing the theorem that I want to prove. Okay. So what you're going to do is you're negating phi. Okay. Put the negated version of phi into the set of formulae on the left-hand side of the inference. And then what you're trying to do is to, at some point, infer false. Okay? So syntactically speaking, this is what we want to do. Because sometimes it is difficult to do it in a direct proof, but sometimes it is more possible, it's easier to do it using an indirect proof. And this is the syntactical view of an indirect proof. But what does it really mean? Okay? In an indirect proof, whenever we see an inference like this one, it means syntactically we're deriving whatever is from the left-hand side to something on the right-hand side. Okay? But that's a syntactical operation. It has no particular meaning, it is just syntactical. If we assume the inference rules are sound and complete, okay, we talked about the soundness of inference rules, okay? In other words, if semantically they all make sense, okay, this has exactly the same meaning as that. It's just that one is a syntactical operation, the other one is representing the semantics behind the syntactical operation. Are we doing okay separating the syntactical operation, which is something that we just did, as opposed to the semantics, which is the meaning behind the syntactical operations? Are we still doing okay so far with that? Okay. Okay, so now we can now focus on just the semantics or the meaning of the highlighted portion on the projector. What does that really mean? Okay, I'm just going to use this particular expression to mean that I have a set of well-formed formulae, T, uppercase T, and I'm using a conjunction to combine every single well-formed formulae within that set. That's all. Are we okay with this notation? It's not dissimilar from the summation notation, okay, except this is a conjunction of every single term within the set T. So what we're doing is we're basically saying, if we combine every well-formed formulae that can be derived, including the axioms, and the negated version of the theorem, that will imply 0. But what can imply 0 and still be true? 0 itself. Okay? If you look at the truth table of implication, okay, when you look at the truth table of implication, x implies y, 1 implies 1 is okay. 0 can imply whatever it wants to, okay? But the only one that is not okay is 1 implies 0. This is the only time when the implication itself is false. So in this case, because we want to be able to imply a 0, right? That means the only time you can imply a 0 is when the first term or whatever is on the left-hand side of the implication is also a 0 or false. And that means instead of doing it like this, we can now say, oh, okay, instead of just implying 0 or implying false, this whole thing has to be false. The entire huge conjunction and that one extra term of not phi, the whole thing has to be false. Is that okay? we connecting from the implication to the equal to? Because in order for something to imply false and still have the implication itself to be true, the left-hand side, whatever this big chunk of thing is, well-formed formulae, it has to be false. Are there any questions about this step? Okay, so assuming there are no questions, we now focus on this one. And we ask, oh, what does it mean when this is false? Well, what about we, instead of looking at what is false, how about we flip it and see what is true? Okay, so we can negate on both sides so that we can say, oh, the left-hand side is true now, and then the left-hand side is also true. So after you negate, one side becomes just one. It becomes the negation of one big, huge conjunction expression, and the other side is just not false. Not false is true, okay? And then the other side, I group all of these into one big conjunction, and I'm not separating these terms into individual terms. So I basically just look at one term and another term, and there's a negation on the outside. Whenever you have a negation on the outside and a conjunction in the inside, you can apply De Morgan's law. After I apply De Morgan's law, it becomes the negation of the big, huge term here, or the negation of the other term, because this term is already negated to begin with, so it becomes double negated after the application of De Morgan's law. Are there any questions about the transformation using De Morgan's law? Okay. The trick of looking at this is not to break apart this whole big term. Okay, just consider this as one thing. Okay, during the De Morgan's law application. Okay, the next one is okay. I combine two steps here. Okay, because the first step is to take out the double negation, because double negation means nothing. Okay, it means you just get the original thing back. But when you have a not something or something else, it is the first thing implying the second thing. Is that okay? And that's the definition of implication. So if I zoom out just a little bit, just so that the font does not overlap each other, so we can go from this step here and use the definition of implication to get to this particular implication. And because this whole thing, we're just saying that this whole thing is true, but we're already saying everything is true to begin with, that is actually implied. So that means equals to true can be left out because that is implied. So we only have this portion left. Okay. When you have this portion left, what does it really mean? Considering T as the set of axioms and all some well-formed formulae that you can derive, what does it mean when those things can imply phi, which is another well-formed formula?
So does that mean that if only if the set of well-formed formulas is true and phi is false, is the whole thing false?
Correct. Which is also saying that phi is a theorem. Okay, and this is proof by contradiction. This is proof by contradiction because we arrive to the same conclusion, okay, that you can find a set of well-formed formulae. All of those can be inferred using the inference rules, okay? And those things together, when you put a big conjunction of those things, they together will imply the new well-formed formula phi, which means phi is a theorem because it is true, it is implied by what is already known. Are there any questions about this? Well, I have a question about this, okay? I'm still not getting it, okay? Because with a direct proof, we get to this one. With an indirect proof, we get to this one too. So what is the difference? It seems like we get the same result regardless. But that's a given, right? Because any theorem has this property. Okay? If I give you something and I say this is a theorem of this particular system, it means it can be implied by all the axioms and other things that you can derive from the axioms. Is that making any sense? Okay. So this by itself, well, let me just re-highlight the portion. This is not the most important part. This is what qualifies phi as a theorem. It's the qualification of a theorem. What is the important part here is how do we get there. In the case of a direct proof, this is how we get there. Let me just highlight the most important part. Is we are using the last step of the proof is one inference to get to phi itself. Syntactical operation to get to phi. Are we doing okay so far with this one? So it's a syntactical operation based on some well-formed formulae that can be derived, and eventually we use the syntactical rules to derive phi itself, and then we prove that phi is a theorem. That's a direct proof. A proof by contradiction, on the other hand, is this is the last step of proof by contradiction. This is the difference. We put not phi onto the left-hand side, and then the derivation, the syntactical operation, only has to get to contradiction. Okay? But the meaning is the same. If we can get to this, we are still saying that phi is a theorem of the known facts of the system. Yep.
Proof by contradiction, though, is just tossing essentially a false in there and seeing if it breaks it.
That is correct.
If the false doesn't break the system,
then you cannot prove.
Then you can't prove it.
Then it is not a theorem.
But if it's like saying, it's like having an unknown value and just tossing something in there to see if it's true or not.
Correct.
The opposite of the known value.
Let me put it this way. Okay, so let's say you're trying to make a machine, and you're trying to mash a new gear into the gearbox. Okay, and the theorem is, I think a 13-teeth gear, is going to fit at this place. Okay, that's a theorem. So if the theorem is true, that means if you put a 13-teeth gear, is it called teeth? 13 per gear, teeth. Okay, so 13-teeth gear into the system, it will operate smoothly. Okay, that's one way to prove it. But the more destructive to prove it is to put something not 13 teeth into that place and watch the whole machine fall apart. Okay, kind of like that. So is that okay so far? I mean, because I do want to put this out first, just so that you guys have a more kind of formal treatment of what is proof by contradiction and why it works. Okay, and also why sometimes it is easier, because sometimes it's easier to come to this particular inference step because what you're working with is different from the other one. Are there any questions about this part? No questions? All right. So this is a new question. I'm not going to make it a homework assignment, but can you think of a way to automate this process? Now that we are seeing it as a spreadsheet, what do you have to do to automate this? How do you implement a program that can do this? Okay, now I'm going to make an assumption here and say that I'm going to give you the parsing subroutine, which is going to be the tedious part. Okay, so I'm going to give you the parsing subroutine so that everything will now be in an array in C or C++ or whatever scripting language you want to use. Okay, so in the end, you just have a big huge array of zeros and ones. Once you have this huge array of zeros and ones, do you think you can write an algorithm to do the resolutions and detect one of two things? One is I can no longer derive any new things and there's no contradiction. And the second one is I can get to contradiction. Do you think this is possible to write an algorithm to automate this process? If I give you the parsing subroutine, which is going to be the tedious part, right? Because you have to parse the open paren, match all the parentheses, and so on and so forth. But do you think that algorithm is going to be a complex one?
This one?
Yep. You're just cross-matching
Yeah,
everything,
it's
right?
just a comparison.
Yep. And if you don't mind your algorithm running a little bit slower, okay, you can just make a double loop. That's all you need to do. Okay, you can just say, for int I equal to 0, I is less than, the number of theorem at that point. Okay, we'll just call it n plus I, and then have a embedding it here for j, int j equal to 0, j is less than n, j plus plus,
It'd be n minus
and
1.
then cross, and then do the checking here.
Would it always be n minus 1 now?
Hmm?
Would it be n minus 1? Otherwise, you're comparing it to itself.
It's less than.
Oh.
You can always compare to yourself. It just won't resolve, right? So this particular algorithm, so you basically just say resolve expression I and j. Put it back into the system. Now you do need a mechanism to detect whether this is creating something new or it is just something that is already in the system. Okay, that is a really important mechanism. But if you keep doing this, at some point, n is not going to increase. You're not creating any new sub-expressions anymore. Then you can stop. You can say, okay, we are done because I can no longer derive any new expressions, and yet the contradiction is not here. You also need a different mechanism to detect that after the resolution, whether it is a contradiction or not, whether it's just false or not. But that's pretty easy because you're just looking for an empty row in the spreadsheet. So that means resolution or resolution by refutation is a very useful mechanism because it is easy to implement, it is powerful, and the best part is it always terminates. One way or another, it will terminate. Right. Are there any questions? Can we do it using a spreadsheet? Now that is a big question.
I don't know if I'd use an array to do this, though.
Well, an array is the easiest way to do it.
Probably just use a tree. That way you
Use
don't
a
have to-
tree.
That way you don't have to worry about expanding or contracting the array. Or linked
Well,
list.
it's always expanding. The array is always getting longer because you're adding new terms to it. You never remove terms from the array itself.
Yeah, I just don't feel like writing a class for an array to expand.
I think, for those of you who like programming, this will make an interesting programming assignment for this class.
I'll give you a linked list.
You can do it in many, many different ways. Many different ways. All right, so if there are no questions about the homework assignment, let me just ask it first, okay? I'm not going to make any assumptions. Are there any questions about the homework assignment? Was it long? And did you take you guys a lot of time? Or
30 minutes, maybe.
But it's mostly tedium.
Yeah.
Mostly just, time consuming. Cross-check this, cross-check that. Yep.
Supposedly trying to type it up in text. That was most of the time.
Well, if you're typing it up, you can use copy and paste, and that helps a little bit.
Yes.
If I were to ask you guys to turn it in as a written assignment, this would take a long time
It
because you
just
have
means
to
you
write
hate
it.
us.
Hmm?
It just means you hate us. Why would you ask us to turn something like that in as a written assignment?
I hate myself too because it would make it harder to read too because some of you do not write legibly. I know because when I graded the last exam, I was having problem reading the first and the last name, and I had to double check using the student ID and say, oh, okay, so that's a V, not a U, or that's a R, not a V, or something along that line.
This person actually
Hmm?
This person actually
I'm going to require everyone to bring a Dymo, to class. Remember those days, the good old Dymo, where you have a little plastic strip and there's a dye that actually kind of warps the plastic to make it turn white. That's the original Dymo. No, you guys are way too young to remember stuff like that.
I know what you're talking
Okay, so now I have to.
I have
it up.
one.
Dymo labeling. And they don't make that anymore, so this has to be like, historical. This one, yeah, that's it. That's one of the original Dymo labeling machines. It does not require any battery, rechargeable thing, or USB connection, or Bluetooth. None of that nonsense.
It's
okay?
thumb powered.
This is thumb powered, exactly. So the plastic thing, you know, the blue thing is actually plastic. It's semi-rigid, okay? And there's a self-adhesive on the back. So you push that thing through the machine and you turn the dial to the letter or the digit or the punctuation that you want. You press really hard using your thumbs, and the die will kind of form the shape onto the plastic, and at the same time changes the color to white, because you know that's what happens when you bend plastic beyond a certain point. And then the machine also has a way to advance to the next character, okay? And then you repeat the process, okay? You turn the dial to the letter that you want to, you know, put onto the label, and then you press, you know, really hard. And some of these even have a special dial position for cutting it. So you turn to the cutting position and you press really hard, and then it will cut the tape or the plastic thing enough, it will score enough that you can just kind of pull it apart, and now you have a, you know, dial label, and you can put it onto your favorite pencil box or whatever. Well, these days you can put it onto your iPhone too. You can say Chris's iPhone.
Get you one of them.
If you can buy one. Only if you can find one these days.
Don't challenge me to that.
All right. So after that, we will go back and talk about predicate calculus, predicate logic. Okay, we started on this one. We are not quite done with it. So I think we are still talking about the terms. So not this one, the next one. New concepts. That's it. This is the long slide that talks about your predicate calculus. Okay, so we'll go back and talk about what is considered a formula in predicate logic. Okay, so this is kind of the same thing as a WFF, a well-formed formula in propositional logic, except remember how I compare the predicate to a proposition. What is the main difference?
Parameters. Parameters.
Parameters, exactly. So a predicate is parameterized or can be parameterized. So here we define what is a predicate. A predicate is a formula. A predicate starts with a notation of the predicate itself. Usually we choose a uppercase letter to represent the predicate. And it can take on any number of parameters. So in this case, it has n parameters. And each parameter has to be a term. Okay, so we'll define what the term is later on. The equality check of two terms is also considered a formula. If you have a formula as phi, the negation of a formula is also a formula. If you have phi and psi as individual formulae, when you combine these two using a connective, which is or, and, implies, or is equivalent to, the result is also a formula. So this part is just copied from propositional logic. But the last part is also useful because you can also attach quantifiers, like for all x, and also the quantifier that exists x in front of a formula, and the result is also a formula. So that's kind of like a recursive definition of what a formula is. We start with a predicate, then we can add negation, we can add all the connective that we know about, and then we can also add the quantifiers. Those are the things you can do with formulae in predicate logic. So the second part defines what is a term. So in other words, what can you pass as a parameter to a predicate? What can you compare in this case? A term can be an element from these particular things. It's actually the same thing, okay? So when we talk about the universe, the domain, or the universe of this course, it is basically saying the same thing. These are the individual elements that can be used or that can be applied to the predicate and the functions. Okay, I will define these items later on. A variable is also a term. Okay, so when you use a variable, you can also consider that a term. The result of a function is also a term. So unlike propositional logic, predicate calculus or predicate logic does allow you to use functions as well. And when we talk about function, it is a mapping from domain that involves the domain here, and it always map it back into the domain. We'll define that later on. Are there any questions about what is a formula and what is a term in predicate logic? These are just syntactical stuff. And the talk about the universe is actually discussed a little bit earlier, okay, right here. So with parameters and functions, predicate calculus also has a concept of a domain. It's also known as a universe and a universe of discourse. All of these terms refer to the same set. Any element of this set can be used to instantiate a parameter of a predicate or function. I have one example all the way to the end of this slide here that will really help to illustrate what I mean by the universe of discourse. All right, the semantics or the meaning of predicate logic. Now, predicate logic is interesting because we have the concept of functions as well as the concept of a predicate. A function in this case, we call it a n-ary function, which means it has n parameters. So a function that has n parameters is a mapping from the Cartesian product of n of the domains to a single domain. Okay, that's a function. When we talk about a predicate, it is an n-ary predicate, which also means it has n parameters. It maps the Cartesian product of n d's into just true or false. Okay, that's a predicate. So a predicate is really, in essence, a function, but it's a special function because it does not map to elements in the universe of this course. It is only mapping to either true or false. All right, so here comes the example, okay, which hopefully will help to illustrate these concepts. So in this particular case, the universe or the universe of this course or the individual elements that I am concerned about in this particular predicate logic system would be these individuals. Okay, so these are names of individuals, and I want to apply predicate logic to these particular people. So we have Mary, John, Paul, Jan, Jennifer, Patrick, Kenneth, Selena, and Cecilia. Okay. D, which is the domain by itself, is not very useful. So I'm going to define a predicate. I'm going to use uppercase P to represent a predicate of father of. Okay, so when you have P x y, if I use the P variable x and variable y, it means x is the father of y. So it can be used to represent a relation in this case. So when you look at the way I define P, which is really a special function, this is how it is defined. I forgot to put extra parentheses, so you have to kind of remember that should be extra parentheses around the pair of names. So in this case, P is really a mapping from D times D, because we are mapping two people into true false. So into true false here. There should be an extra parentheses, extra pair of parentheses around John and Paul, and also around John and Kenneth. So what this means is John is the father of Paul, but this means John is not the father of Kenneth. Are we doing okay so far as in terms of understanding what how predicates are defined? Okay. Now you can also have predicates that have no parameters. Okay, if the context warrants it, you can have a predicate that has no parameter, which basically makes it boil back down into a proposition, because it's just saying, okay, a particular fact that is either true or false by itself. So in this particular set, because we have 9 people, if you count, there should be 9 people here. So that means the predicate P should also have 81 elements, because it is going to express either true or false across all possible combinations. Any questions at this point? Questions? All right. So we're going to define Q, and Q is a predicate that means mother of. Okay. So in this case, we can define another predicate Q, which is also mapping from the Cartesian product of D and D into true false. And I'm not even going to give you that example because it's just going to be really long. I mean, it has 81 entries, and each entry has 2 names and 1 or 0 after that. R is ancestry, okay? So if I want to define R to be the ancestor of, okay? So here is how things becomes kind of interesting, because if you know the relationship, the parental relationship of everyone in this list, can you use that to deduce ancestry? Does it give you enough information? What do you think? If within a group of people, okay, do you guys have any questions? Okay, so within a group of people, if you know who is whose father and who's mother, okay, can you establish ancestry information across any two people?
Yes.
At least you can tell, yes, this person is an ancestor of that person or not. It should give you enough information, right? So we'll go ahead and see how we can define R, or what is a property of R in this case. Okay, so let's take a look at this one here. For all x, okay, now whenever we say for all x, it is already implying that x is an element of D. Okay, x has to be an element of the universe of this course. And the same thing applies to for all y. So y has to be an element of this course, which in this particular context means x has to be one of the 9 people that we are talking about. Y is also one of the 9 people that we are talking about. Okay. The first one is basically saying if x is the father of y, or x is the mother of y, then R is also true. Okay, it's an ancestry. Okay, now we normally don't call our parents ancestor, right? But strictly speaking, they are, an ancestor. Does the word ancestor imply that person is dead? I don't think so. I mean, because it's just saying that it is linked by parenthood. Okay, so this is the easy one. This is the easy one. A parent is also an ancestor. That's basically what it's saying. What about the other ones? What about the recursive definition of ancestry? So here's the recursive definition of ancestry. So here we have a z. So we're introducing an additional variable, which is also one of the 9 people. And the first part is the same as before, but this time we are not relating x to y anymore. Now we are relating x to z. So z is basically an intermediate variable. And we are basically saying if x is the father of z, or q, or x is the father of z, a mother of z, and in this case, we also have an and z is an ancestor of y. Then, we also conclude in this case that x is an ancestor of y. Okay, is that making any sense? Okay, let's think about it. Okay, so we have x being an ancestor or father or a parent of z. Okay, so x is a parent of z, and z is an ancestor of y. Does that make x an ancestor of y? It does. So this is kind of a recursive way to define a relationship, okay, or in this case, a predicate.
Why is the first half necessary?
The first half is necessary because you need the recursion to terminate at some point. If I don't have I'm assuming when you said the first half, you are referring to this sub-expression. Yeah, that sub-expression is necessary because otherwise you can have endless recursion. Because the reliance on R is through a conjunction, so that means that means you cannot avoid it. And this is the only way to avoid it is to make the first expression true. Then with lazy evaluation or short-circuit evaluation, then you don't have to evaluate the second part, and therefore you are avoiding the recursion when you do not need recursion. Are there any questions about this particular example? Yep, go ahead.
What's the symbol before the first Z?
The symbol before the first Z. There exists.
Oh, there you go.
You mean the inverted uppercase E?
Yeah.
Yeah, there exists. Okay. So in this case, we are basically saying there exists a Z, which is a parent. Okay, X is a parent of this intermediate person, but that intermediate person is an ancestor of Y. Then we can establish the relationship of X being an ancestor of Y. Is that okay? Now the implication is also important because the implication is actually this is the open paren and this is the closed paren for the equivalence. So that means for each X and for each Y, it has to meet this requirement in order to be called an ancestor. And as a result, when you have X and Y being the same person, it is not an ancestor. It is not my own ancestor because it will not be able to meet either one of these requirements. Is that okay? We are almost running out of time, but it is a good time to mention, what if I tell you all of this stuff here can be done using a particular programming language? There's a programming language designed specifically for this purpose.
Prolog.
Prolog, exactly. Okay, so some of you may have encountered the Prolog programming language. So if you look at Prolog, there are many implementations of Prolog. One that is free is called SWI Prolog, and I think it is available for all platforms, for all versions of all usual operating systems. So when you look at download, go. So it's available for Windows, for Mac OS X, and also for Linux. It's not a very difficult programming language in terms of syntax, but it is difficult to do certain things because it has no concept of a loop. Yeah. Go ahead. But I think next time what I'll do is I will show you certain examples of using Prolog because you can use it to answer questions. In other words, you can, after you enter all the facts into the system, like who is whose father and who's whose mother, and you set up the rule of ancestry, you can now say something like ancestor, and you can specify Tom, assuming Tom is one of the elements in the domain or universe of this source, and now you can specify an underscore here, and it will come back and say Tom is the ancestor of all of these people. Or if you specify a particular person, it will come back and say true or false, whether Tom is or is not an ancestor of Mary. Or you can say underscore here and then Mary here, then it will list all the ancestors of Tom. So the Prolog interactive environment actually is an inference engine that can take all of the predicates that you have entered and apply all of those things in a not only recursive way, but also in a, okay, what is the term of that? It's an exhaustive search mechanism. So it will go and find all possible solutions when you have an underscore in front of the position. It will find everything that fits this particular description. So from that perspective, it's a very interesting programming language. It's not like Lisp, it is a competitor of Lisp, but it has a built-in nature to exhaustively search for solutions, which makes it kind of useful and interesting. Right. So we are running out of time today. You guys have a nice weekend. No homework until Tuesday. So, and then I'll have to think about whether to give you an assignment with Prolog or implementing resolution. Yep. All right. So is it homework?